Thanks, baby. Let's do some science. We got some flasks here with some universal indicator in them. Let's add a little bit of hydrochloric acid to this one on the left. I think this one on the left might be buffered. Let's try adding some here to the one on the right. Look how much quicker, how much more quickly the one on the right changes color. That's the unbuffered solution. Here's our buffered solution. I'm adding drops to the buffered solution over here. Yeah, that's taking a long time to change over there on the left, isn't it? Let's see here. These are the different colors that you can expect to see. What's going on, Gigabean, Arjun, Isaiah? These are the colors we're going to see. Oh, we don't have any elephant toothpaste, man. I'm in the basement. Just doing some color changes. We could do the color separation. Let's do the color separation. What the heck? It's been a while since I've done that one. All right, I hope this works. I'll try this bottle first, huh? Let's see what we got going on over here with this bottle. Okay, happy Easter for those that celebrate. All right, let's add a little bit of, we're going to go purple food coloring to this fluid here. Go like 1 drop, I don't know. Maybe 2, huh? 2 drops. Looks pretty, doesn't it? Hello, Carly. What's going on? 2 drops of food coloring to our bottle. Looks like kind of Easter color, yeah. Purple's an Easter color, lavender. We'll shake this thing up, get the color to go all the way through. I'm going to do a salting out experiment. So what I'm now going to do is I'm going to add some salt to this fluid. And we're going to see what happens. Here we go. Get my funnel so it goes in a little easier. In goes the salt. And let's shake this up and see what happens. What do you think's going to happen, huh? I don't know. We got to find out. The water, or I don't want to say the water. Although there is water in here. I should say the fluid. Because there actually happens to be 2 different liquids mixed together in this bottle. The 2 different liquids are acetone and water. And to that mixture, I have added some salt. I like my pizza. I like my pizza with the crust. This shouldn't explode. This mixture of acetone and water also has some purple neon food dye added to it. And I've also added some salt. And I'm trying to shake it up to get the salt to dissolve in the fluid. And it turns out that when you do this, the salt and the water mix together really well. There's really strong attraction between those 2 compounds. And then the salt and the water will, in a sense, bind exclusively, and they should push the acetone layer out. Sure enough, we're observing that in real time. So you can see 3 different layers. This is the salt water layer. This is the acetone layer, and in the middle, there's a mixture of the 2. We call that the emulsion. It's a beautiful experiment. Isn't that cool? And now it's separated into an acetone layer on top and a saltwater layer on bottom. The violet dye, by the way, it's made of 2 different food dyes. It's made of red food dye. It's actually red dye number 3 called erythrocene, and blue dye number 1. And it turns out the blue dye dissolves better in the, hello there, Aeon. The blue dye dissolves better in the saltwater layer, and the red dye number 3, erythrocene, that dissolves better in the acetone layer. We call this salting out. So you'll notice I added salt to the mixture of water and acetone, and the acetone layer was what we call salted out. Now I'm going to shake it up, and when I shake it up, you'll notice that the blue and the sort of pink, they mix to make a violet. So there's a single layer of violet. We call that an emulsion. It's a temporary mixture of the salt water and the acetone. And now you can see all three layers. We see the acetone layer up top, we see the saltwater layer on bottom, and we see the emulsion layer in the middle. I'm not drinking that. No, not gonna happen. No way I'm drinking this. But I thought it might be neat to try some other colors. I have no idea what's gonna happen if we try some other colors. I have some neon blue, neon green, neon pink. And what I'd like you to do, this one's the neon pink one, this one's the neon green one, and this is the neon blue one. I'd like you to drop in the chat which disco party, which color you would like to see me test next. And I honestly have no idea what's going to happen. So we're going to repeat this experiment, using, again, a mixture of a mixture of acetone and water. So Amy's going green. Nancy says red. Sydney says blue. I see 2 votes for red, 2 votes for green. 2 red. Oh, it's all even. It's 2-2-2 right now. 2-2-2. I'm seeing blue getting up ahead here a little bit. Yeah, blue, green. Oh boy, here comes green. Wow. Well, I have 2 different bottles I can try. It's looking like blue is taking it, so we're going to try it with blue, okay? We're going to try the blue one first. LU, I can do 2 colors. Let's do blue first and see what happens, okay? So we're going to do blue first, and I can go ahead and add the second color. All right? So again, this is a mixture of alcohol and water. Acetone and water, to which I'm going to add some neon blue food coloring. In it goes 2 drops. Ooh, that's pretty, isn't it? It's pretty to watch that drop like that. Now I'm going to go ahead and mix this up. It's just a beautiful color. Look at the way the wisps just kind of go down. Here we go. Let's mix it up. All right. And then we're going to do the same thing we did last time. I'm going to add some salt. And this will cause the acetone to salt out because the salt and the water bind together so strongly. I like to say it's kind of like, when 2 people have real strong attraction for one another, they will start to date exclusively and push everyone else out. And in this sense, when I add the salt to the mixture of acetone and water, in a sense, the salt and the water begin to, quote unquote, date exclusively, and they push the acetone out. And that's because there's strong forces between the salt ions and the water molecules. Here we go. Let's see what's going to happen. So again, what I'm mixing here is a little bit of salt into a mixture of acetone, water, and dye. And we're going to see what happens. And honestly, I've never done this before. I have no idea what's going to happen. This is what happens. This is what happens when I try this experiment with some neon purple food dye. The salt water separates from the acetone layer, and the blue from the violet goes into the saltwater layer, and the pink from the violet ends up in the acetone layer. I have no idea what's going to happen here. No clue. It might be a dud, I might not see any color separation whatsoever, but we're going to just give it a shot and see. Let's see what happens. Is there anything going on? I think there are 2 different layers. It's really difficult to see. It looks to me, if you look up here, you might notice that the acetone layer is a little lighter and the saltwater layer is a little darker. Now, this is not an exclusive separation. It's not an exclusive separation, so there is a little bit of the blue dye that ends up in the acetone layer, and most of the blue dye ends up in the saltwater layer, but it's not a perfect separation. Yeah, it looks a little like a gradient. I'm going to shake this a little more to see if I can get all of the dye out of the acetone layer. I'm not sure about that. What's going on there, Helping Earth? Amy says it looks like a gradient. Nancy says it's good to experiment, which is what we're doing. We're going to try it one more time, too. So here we go. Let's see. Let's see if we can get a little better separation of colors. Hello, chicken nugget. Yeah, it looks to me like that faint amount of blue is going to remain in the acetone layer. We can really easily see the 3 layers now. You can see that acetone layer on top. You see that dark saltwater layer on bottom. I guess it is a little tough to see the faint medium blue emulsion layer. Hello there, Otso. Hello, UDG. I'm now going to add, I'm going to try this one more time. And we're going to try it because this separation wasn't perfect. I mean, it looks kind of neat, but I like the real sharp separation. Maybe I'll shake it one more time. Hello there, Sydney. Just to see if we can't get all that blue dye into the saltwater layer. I doubt it's going to happen, but I don't know. I'm just going to keep trying here. See if multiple extractions. No, it's still pretty much that same sky blue color. Hello, Helping Earth. Okay. All right, we're going to try pink. Let's try pink. That's the last one I can try. I got one more bottle ready. And then we can go on to this experiment over here, which is kind of neat. Yeah, we got a separation, but not as nice as I was liking. Okay, last one. Last bottle here. We'll give this one another shot. I'm going to try to get in a little closer so we can focus on the experiment a little more. I'm going to go ahead and open this one up. And we're going to try, a lot of people wanted green, I think. Green was second place. So we're going to add drops of green to this one. Here we go. 1 drop of green dye. Another drop of green dye. And let's see what happens. Let's see what happens. We did do the blue. Stein, we did do the blue. That was this one. This was blue. All right. We did that one, Stein. I'm going to go ahead and shake this up. See what kind of color separation we get. Oh, that looks kind of yellow-green, doesn't it? Okay. Hello, Chicken Nugget. Here we go. I'm going to start adding salt to this. We're going to see the salting out effect take place. Now, what you're looking at right now, if you're just joining us, that is a mixture of water and acetone, a little bit of dye added. I'm now going to add some salt, and the salt and the water are going to mix very well. And in fact, the attraction between the salt and the water is so strong that they bind to each other exclusively, and they will push the acetone layer out. So here we go. Let's see what happens. See if we get a nice color separation with this one. And then we can add some food dye to some of the other bottles that I've made. What's going on, Moebius? Stein, we can do pink, but unfortunately, I only had 3 bottles prepared. Sorry about that. I can add pink to this one, though, or to the blue one, so we can get a feel for what might have happened. We can do that. Here we go. Let's get this all nice and shaken up. Let's just see if we got a little idea what's going to happen here. I can still see some undissolved salt. I don't think we're going to get much color separation. Oh, yeah, look at that up there at the top. Look at that. I think the acetone layer has no dye in it. So in this case, the acetone layer is almost colorless, which means most of the dye is not in the acetone layer. Most of the dye is in the saltwater layer. Thanks, Erstein. John King, I know how to get hydrochloric acid easily. You can find it at if you know what you're looking for in a hardware store. If that's if you're just trying to find it. You can also find sulfuric acid in hardware stores as well. But you ought to be careful using that stuff. You can burn your lungs if you inhale fumes of hydrochloric acid. All right, let's see what this does here with this bottle. So again, what you're looking at is a mixture of water, acetone, salt, and dye. And when you do that, when you mix this, the salt and the water mix together so strongly, there's such a strong attraction for them, that the acetone gets pushed out. So this is an acetone layer up here. And we also notice that the dye doesn't end up in the acetone layer. That's a pretty nice separation. It looks like pickle juice, says Amy. I agree. Hello there, Alana. I think we got a pretty nice separation there. Yeah? That looks kind of neat. It's similar to the separation we got with the purple neon. That's gorgeous. You know that's gorgeous. And then, of course, with our blue dye, we didn't see a whole lot. Yeah, that blue dye is kind of disappointing. But what we're going to do now, I think, I'm going to go ahead and add to this one here. I'm going to add some of the neon red dye. And I'm hoping that the red will end up in the acetone layer like this. And then we'll get to see a red-green separation. That's right. See in the acetone and water, there's a certain density, but when the separation happens, this is basically the density of acetone. And this is basically the density of salt water. Salt water is more dense than acetone, which is why this is floating on the bottom. Let's go ahead and add a little bit of. Oh wow, what was that? There's a bunch of salt in the bottom of the cap. Okay, here we go. I'm going to add a little bit of red now. Wonder which. Look at that. That's pretty freaking cool, man. Oh, you can even see it going down into the saltwater layer, but you can see that the dye that I added is more dense than the acetone. It's sunk to right here, and it looks less dense than the saltwater layer. I agree. That was pretty cool. That was a nice effect. We can do that probably with a blue one, too, and see some interesting effects. So I'm going to go ahead and shake this. Let's see what happens. All right. Here we go. What's going to happen? I don't know. Where's the red dye going to end up? It looks kind of orange now. So it looks like we've made an orange fluid. But remember that orange fluid is a mixture of salt water and acetone, and that's not going to stay mixed forever. That's an emulsion. An emulsion is a transient mixture, kind of like what happens with salad dressing when you first shake it, and then it separates. Let's see what happens with this separation here. Oh, look at that. The pink dye went in the upper layer as predicted. Look at how gorgeous that is. Hello there, Joseph. Come on, man. That's freaking cool. I think a little bit of pink went into the bottom layer as well because the bottom layer is no longer green. It's got changed to an orange color. So there must be some red down here. There has to be. But still, that's a really cool separation that we got here. It's beautiful. I think we're going to be able to do the same thing with this, right? I'm going to add a little bit of pink to this. Yeah, we'll add a little bit of pink to this one, and the pink should end up in the upper layer. So let's try that while we're watching this separate. The same thing should happen here. Wow, that's cool. That's really pretty. It looks like those lava lamps. Thank you there, Helping Earth. Looks like a sunset, says T. Boogie. Hello there, Kaname. Try green. We did green. This one, believe it or not, this one was green. And what it basically looked like is most of the... hello there, Yash. Recognize you. We did this one, which was green previously. K-A-9. K-A-9. Okay, here we go. I'm going to add a little bit of pink to this blue one. And it goes. Kind of see it drop to the interface between the two liquids. The top liquid is acetone. The bottom liquid is a mixture of salt and water. And we're going to shake this baby up and see what happens. Here we go. Hello there, Diamond. Oh, it won't take long, Hotel. Here we go. We'll shake that baby up. Shake it up, baby. All right. That's a gorgeous looking mixture of blue. It's like some kind of electric blue. And look at that. We've already got the separate. Look at that up top. We've got kind of like a violet on top. And we've got blue on bottom. So we've got some interesting colors here today with our new experiments that we did. mixing food dye, acetone, and water. That was kind of fun. Yeah, that is pretty. Look at the different colors we got. How does it work, Hotel? So what we've got is, first you take a mixture of water and acetone, which mix completely. You add some dye. In this case, we added both blue dye and a violet dye. All right, so, excuse me, a blue dye and a pink dye. And then to that mixture, you add salt. What happens when you shake it up, when you shake up the mixture, so this is, it's got everything mixed up. But what happens here is the salt and the water are so strongly attracted to each other that they push the acetone out. So the acetone layer ends up on top, the salt water layer goes on bottom, and then the dyes, they partition, so to speak, they separate into whichever layer they dissolve in better. And it turns out in this case that it looks like the red dye dissolves fairly well in the upper layer, and the blue dye dissolves in both layers. So the bottom layer looks blue, the top layer looks violet, because both the blue and the red is going to give you a violet color. So you're welcome, okay, or Hotel. This is not an alkaline bottle. This is the other color separation we got, which I think is gorgeous. And the third combination we got was this one right here. Aren't those pretty? I think those are absolutely beautiful. They are immiscible liquids. So salt, water, and acetone indeed are immiscible liquids. Nice. A chemist has entered the chat. Thank you. They're grateful. Let's get back to doing some acid-base reactions, experiments. They all look tasty. I wouldn't drink it. Man, you don't want to be drinking acetone. That's going to ruin your afternoon. All right. I don't have any eggs with me. Apologize. We're not going to do a bouncing egg experiment, but man, that'd be a great experiment certainly to do for those that celebrate Easter. I just don't have the materials. Hello there, malware. All right, here we go. Let's add a little bit of acid to this flask. The acid I'm adding is hydrochloric acid, which is the same acid that you find in your stomach. It just is a lot more concentrated. I got you, T-Boogie. It's okay. I love getting suggestions. Okay, so now you see the color's red. The color's red because our pH is 3. We've got an acidic solution. That's quite acidic, right? The further you get from 7, the further below you get below 7, the more acidic it is. We are now going to start adding base to this. Oh, nice, Amy. Yeah, that is a great experiment. The rubbery egg experiment. We're going to start adding a couple drops of base to this, which should neutralize the acid. There it goes right in the middle. See what we get. Excuse me, a little flash of the rainbow, baby. We got the rainbow going on, folks. Love it when that happens. Love me the rainbow. Really pretty. Thanks, Sarah Darwo. Make a compass. That'd be fun. Hey, Moibus, thanks. Yeah, so all I'm doing right now is adding either acid or base to our flask. And when we do that, the acid and base react with each other and they neutralize each other. And so that's why you're going to get all these different colors. Someone tried to do electrolysis in pure water and the water turned yellow. Is that because of dissolved chlorine? John King, it could be. Dissolved chloride ion is colorless. My guess, John King, is that you were using electrodes that had iron in them, and the iron electrodes started to dissolve, because when iron dissolves, it will often form yellow-colored solutions. Tell me if you used electrodes, metal leads that contained iron, and if not, we can take another guess as to what caused the yellow color. Do bluish purple. Okay, to do bluish purple, we have to get pH 9 or 10, which means I've got to add quite a bit of base. So right now we are, like pH 7 or 8 in this region. So I'm going to start adding zodiac chart. Come on, man, this is a science channel. So, John, that's probably what was going on. Some of your iron rods dissolved, and that caused the yellow color. There's a little blue-violet for you, huh? It does, Amy. These are very concentrated solutions of acid and base, which is why the colors change so fast. But we can do this. This is kind of fun. We can, we can do the slow change. To do the slow change, what we do, first I'm going to make everything acidic by adding a bunch of acid. Hello there, Philip McNugget. I'm adding a bunch of acid here. The acid I'm adding is hydrochloric acid. That's the same acid that's found in your stomach. Thanks there, Cynical. We're going to turn off the stir bar. And then I'm going to just add some drops of base. A glowing egg experiment, says Hotel. I don't have any materials for that. I'm going to go ahead and add a few drops here of base. And we're going to see what happens. We are going to see what happens as the base kind of falls through the solution. The acid and the base should react with each other. And we are going to see, look at that. Look at that color. Just beautiful, huh? Cynical, thank you. I appreciate that. Cynical subscribed, I appreciate that. I think we reached, I don't know, maybe it was early this month. We hit over 600,000 subscribers, which is a lot of fun. Isn't that beautiful? Let's add a little bit more base. Nancy, great question. Do you think this will stay this way the next day? You know, I can set that up and let you know. Maybe at the end of the live, I'll do that, all right? We'll set up the experiment and just let it set and see what happens. Like when you look inside a bubble. Turn off that stir bar over there. It's making a bunch of racket. Hello there, Lego Brick. Hope you're doing well. Yeah, it looks like we got a lot of interesting stuff going on. Looks a little like a lava lamp. Let's see what happens over here. This one's same thing. Over here, we'll do this. Over here on the right, we have the same thing going on. We have a, it's just a flask to which water and universal indicator has been added. And then I just add acid or base to it. This one's spinning, this one's not. We're kind of developing over here, man. We're developing a static rainbow, which is just gorgeous. Very pretty. All right. Moibus. I wouldn't know, Moibus. Bath bomb experiment, huh? Yeah, we could do that. I think I got some stuff where we could do a bath bomb experiment. I think one of the most interesting elements to exist is fluorine. This thing reacts with just about anything. That's pretty nasty stuff for sure. I'm adding base to this flask over here on the right now. Got a nice violet color. Dip my finger in it. Probably not going to do that. And now I'm adding acid to the flask. We got a little flash of the rainbow, baby. Hello there, Wall. A little more acid over there. Thanks there, Friendly. Appreciate that. Welcome aboard. We just, we do some really simple... Look at this over here, Friendly. Isn't that gorgeous? Look at that little tornado-like wisp down there. If I was an element, which one would I be? I'd be hydrogen. I know that might be weird with a name like Tommy Technetium. You're probably expecting me to say technetium, but I love hydrogen. So how do we get this reaction? What I've done is I've simply added universal indicator to both of these flasks. Universal indicator is also known as rainbow indicator. Cynical. Philip would be palladium. Universal indicator displays these colors at different pH values. So we can see this is yellow, so the pH in this particular system is currently pH 6. Yash, I'm using phenolphthalein in addition to 3 other indicators. Thanks, Air Friendly. Glad to hear that. And then if I add a little bit of acid to this system, hello there, Stein. Let's add a bunch of acid over here. And you'll notice that the color shifts from yellow to more orange. You got it, Adam. And if I continue to add acid, it'll shift to a red color, which indicates like pH 3. Hello there, Majestic. So great question, The Wonder. If the pH is neutral, is it dangerous to drink? If there were no indicator in there, it would be salt water and therefore not dangerous to drink. Thanks, Airwall. Welcome aboard. Feel free to ask whatever you want. The issue with trying to drink this when it's neutral is one of the indicator dyes is a laxative, and it's a pretty strong one. So Stan Lee wants to know what's going on and how we get the suspended color. Stan, I'm going to show you that here in a moment. So what I'm going to do here is I'm going to stop the stir bar. All right? And Stan, feel free to ask if you want to know how we get the red color and all these other colors. Hopefully you've been on board to hear that. And now what I'm going to do, after this kind of settles a little bit, I'm going to add base. Here we go. You're going to see right here, I'm going to start adding base. Drops of base. You can kind of see the violet color grow in. And then we just let it sit. We just let nature do its thing, man. That's all you do. That's exactly what I did to get this. You just got to be patient and wait. What do I think is the most interesting salt? What do you think, John King? Let's see, the most interesting salt. This is going to sound funny. I think your teeth. Your teeth are a salt. They're made of calcium hydroxyapatite. So the formula for that would be 5 calciums, 3 phosphates, and a hydroxide ion. We call that salt apatite, or sometimes, hydroxyapatite. Sometimes we just call it calcium hydroxyapatite. And just like any inorganic compound, it's a salt. Look at that. Isn't that gorgeous? All right. Looks like I kind of missed this one. I think I added too much base. I'm going to go ahead and... The salt that goes on pasta, says Amy. I love it. Sodium chloride, huh? Amy's favorite salt, sodium chloride. Well, T-Boogie, I want to be real careful here. Technically, yes, your teeth are a salt. So a chemist, to a chemist, any inorganic compound is considered a salt. And so because your teeth basically are made of inorganic ions, it's a salt. It's made of calcium ions, phosphate ions, and a hydroxide ion. Okay, here we go. Let's see if we can do this again. I'm going to try to add a little less hydroxide here. Here we go. I'm going to add like 3 drops this time. 1, 2, 3, and let's see what happens. So we can remineralize our teeth. What a great question, Avil. No, you cannot once you have a cavity, okay? And here's why. Because there's not just chemistry going on in your teeth. There is also biology happening in your teeth. And what happens is your teeth have a film that form on them, and there are bacteria in that film, and that film protects more salt precipitating out on your teeth. And so that prevents, once you get a cavity, that prevents that cavity from being able to be remineralized. And you might think, well, that's kind of crappy. Well, actually, if you think about it, it's not. Because just imagine what would happen if you could remineralize your teeth. We would have little pockets, little shards of new precipitate of the salt that makes up your teeth that would continually be precipitating out on your teeth. Kind of like stalactites and stalagmites form, that would be happening on your teeth. So instead of the nice smooth surface that you see on your teeth, there would be these little jagged rocks that would be forming. That's kind of cool, ain't it? Huh? It looks like I think what's happening over here is I'm adding it too quickly. So I'm going to try this again. Well, thanks for the question. Thanks for the hello there, Rock and Rolla. It looks like the acid and the base almost perfectly neutralize each other, giving us a green color. Green is pH 7, so we've neutralized it. No, I don't think that means we'd have bone cancer, man. I don't understand the question, Hillary. You said, so it's harmless for the teeth. I apologize, I don't understand the question. And I'm also, folks, I'm not a dentist. I'm just somebody who has studied I've studied the chemistry of teeth a little bit. Appreciate the vote of confidence there, Tom, but I can assure you I am definitely not the new Albert Einstein. Far from it. I know what I know, and I know what I don't know, and I do not know what that man did. Brilliant. Brilliant man. I can understand some of his stuff, but once I get to general relativity, I need some help. The grandchild of Einstein. Come on, man. Okay, we're going to add a little bit of base to this once it settles down. Do I have mini glass plasma bottles? I have a plasma ball that I mess around with every once in a while. That's kind of fun. Okay, I think we might be ready. I think this might have calmed down. Let me try to add 1 drop, 2 drops. This is going to work. 3 drops. You can see it sinking. 4 drops. I don't have any bromine friendly. I do have some in my lab that I use, sealed in a tube. I've done a video on that. Okay, we're going to see what happens now. All right. Oh, you got it. That's cool, Amy. All right, over here, we're going to go ahead and we're going to... I don't rock and roller. I apologize. I don't know how to make fireproof paint. Do you? I don't have chromium chloride. I don't mess with... There's some stuff I just don't read with. Or excuse me, mess with. Have you ever read about plasma jet method for synthesis of nanoparticles? I've not, Yash. What do you know about that? Tom, what changes the color is I have added to both of these flasks something known as universal indicator. Universal indicator is also known as rainbow indicator, and it changes color depending upon pH. These are the different colors it displays at different pH values. And what's kind of nice about this flask is we're seeing all the pH values. How you doing there, Artur? We're seeing all the different pH values in this flask. Here's what we're seeing over here. We're just seeing 2. But what's really interesting about this... let me talk about this one just for a bit. In this particular flask over here, you see both red and violet. And that's interesting because red indicates pH 3, 10 indicates, violet indicates pH 10. So that's it. Thank you for the sub, Artur. So the difference in pH between these two is 7. Sorry, Hotel, I don't have that here with me. I have made nitrocellulose elemental, fun stuff. Now, the significance of that is the pH scale runs on powers of 10. So the difference in acid concentration between the top and the bottom is 7 pH units, which, because it runs on powers of 10, is 10 times 10, 7 times. Well, 10 times 10, 7 times is 10 million. So what's really cool about this, in this flask, we are looking at a difference in acidity between the top and the bottom of a concentration of 10 million times. And indeed, Tom Walker notes that in the middle, it looks multicolored because we're getting, it's a slow gradient from one to the other in the middle. So, okay, Nancy wants us to leave this until tomorrow. And I think I'll go ahead and do that. We're going to go ahead and leave this till tomorrow and see what happens. All right? I'll take a picture of it and post it online. Come back. I got to remember to do that. So Yash is taking an exam on the chemistry of cosmetics and perfumes. That's interesting, Yash. I've recently been I'm going to go ahead and stir this one up. I've recently been thinking about, the chemistry of the makeup that people put on their face. And it blew my mind to learn that blushes that, people put on their face, those are generally iron oxides, right? Like the red is from basically rust. I think that's what I heard. And then I guess they can add a little black color from black iron oxide, yellow iron oxide. And of course, there's red iron oxide that gives a variety of colors, from what I understand. So, Yash, tell me if I'm wrong about that. All right, let's add a little bit of... Thanks, here, Stan. I appreciate it. Going to add a little drop of base there. Mainly oxides. Thank you, Yash. And it's mostly iron oxides. Is that correct, Yash? Isn't that crazy, Amy? Yeah, I know, right? When I heard, I was like, that's crazy. I do not, Hotel. Elemental. I just use my iPhone 14. I just use my iPhone 14 for all my films. Isn't that great? Yeah, people put rust on their face unless Yash is the one who's studying this. So it's just what I understand. But, I'm not an expert. This isn't something I think about every day. Not mainly iron oxides. Thank you, Yash. But oxides are used. Yash, do you happen to know which oxides are used? So Roy's jumping in. Hey, Roy, what's going on, Roy? Roy's telling us that rust pigments work well in fresco paintings because they're stable in the lime. That's right. I think that's right in the DIA, Roy. That one particular artist where that huge mural is. That huge mural is on lime, correct? It's muscovite. So, Jordan, give me a little more information. So it's muscovite and eyeshadow. Hello there, Henry. Please don't spam the comments or I block you. Roy's here. Roy's an artist, so he would know quite a bit about that. Giving you one more chance here, Henry. All right, see you later, buddy. See you later, Henry. Henry is gone. Yeah, don't be spamming the comments or you're gone. It's just, come on, man, right? Friendly has a project on chemistry, optimizing nuclear thermal propulsion rocket systems for school. So you got to learn about the different types of that. Thanks, Amy. Thanks for the subscription. Hello there, Candy. Yes, Artur, I am a scientist. So titanium and, are you sure? Yeah, they're using chromium oxide. That doesn't sound right to me. Hello there, Candy. Please don't spam the comments. Hello there, Jensen. Andrea, we're going to block you pretty soon here, too, so don't be spamming the comments, please. So long, Wall. We'll see you next stream. There they go again. Yep. I am, Artur. I am a scientist, indeed. Yep. I'm adding acid right now to get a nice red color. Check out what's going on over here. Hey, look at that. That's kind of cool. Interesting. Titanium oxide has 3 polymorphs, and I think rutile is the one that's used in food additives and cosmetics. What experiments do I recommend for an amateur chemist? Well, I'll tell you what. Just honestly, get on my YouTube channel. There's a whole bunch of amateur chemistry experiments that you can do. If you look at some of my old stuff, I spend a lot of time talking about how to set up and carry out experiments. Rutile, anatase, and brookite are the polymorphs. Jordan, those are used on the, I'm going to take a screenshot of that because I'm going to come back and visit that later. No, I'm not making lava lamps. A hotel. I do not have any right with me offhand. Unbelievable. What I'm doing is I've added universal. I am a chemist, Asmit. I've added universal indicator to both of these flasks. Hello, random guy. And then I just add acid or base and watch the beautiful color changes that occur. And then I talk to folks. We talk about science. I tell people what I know, what I don't know about chemistry, and people in the chat, they tell us what they know about chemistry. That's all right, Jordan. You should take what everybody says with a grain of salt. But, you should, in my opinion, you should listen to the experts they're more likely to be right than anybody else. Doesn't mean they're perfect, but they're more likely to be right. Hello, Jensen. Hello there, Lisa. Thanks, you're unbelievable. Artur, you feel free to add me on Snapchat. I don't do a whole heck of a lot of stuff on Snapchat, just so you know. Thanks, Jordan. I appreciate that. Glad you're turning your brain on and thinking. But please, please don't think I'm an expert in... I do have a PhD in chemistry, I'll tell you that. Zinc oxide and titanium dioxide are in face powders, says Yash. So zinc oxide, I imagine both those and titanium dioxide, those should give you a white color, correct? Can I name a car for an edit? Please, I will not disappoint, like any supercar, please. That random guy, I apologize, I don't understand the questions. You just want me to, name some kind of car? I hear you, Artur. Welcome aboard. Make a fruit battery. Hey, hotel, check through my shorts. instead, a lot of people make a fruit battery. I made a Play-Doh battery. You can make a battery using Play-Doh. Nice, Yash. So that, I imagine that those are going to give a lighter color. Oh, okay, like a Ferrari or a Lamborghini. How about a Corvette? Do I work or prefer any specific category or field of chemistry? How'd I get into it? Do I like chemistry in school? We just covered stoic at our school, but my teacher left mid-year. Not going to happen, Gecko. Hello there, Caden. Interesting, Stanley. So what got me into chemistry? I was in college. I had to take it. And I had a professor who did some chemistry experiments. It was the first time in my life I ever saw like some interesting colored. Hello there, HWK Pikachu. I got to see some beautiful color changes, and I was mesmerized. And right then and there, I'm like, I think this is what I want to do in my life. I want to do science experiments for people. And that's what I'm doing. So all of you folks here, all 38 of you, you're helping this old man's dreams come true. I'm still old, I'm still doing it, and it's still what I want to do with my life. I love doing science experiments for people. So thanks for helping my dreams come true, everybody. And I'm not lying. That's the total truth. HWK Pikachu, how's it going, man? No, Arthur, I have no idea how to fix cars. I'm the last person you want to ask about fixing cars. Absolutely the last. Thanks for being here, friendly. Thanks for hanging out. I'm good there, Pikachu. Make a fizzy wobbly. Let's try it. I got some stuff. This is giving Gecko, huh? I'm not a Breaking Bad kind of guy. I'm like a happy mad scientist. All right, so somebody wants to see like some fizzy stuff. So let's do some fizzy stuff, huh? I think I got some stuff to be able to do that. Thanks for the sub, Artur. I appreciate that. Oh, my legs. All right, I just stood up. Let's try this. Okay. What am I going to do here? I don't know if I have a... Let's try this. Let's look at our static flask here for a bit. Isn't that nice? Look at that. It's just like a... I wonder what's going to happen to that overnight. Artur, I don't have stuff for a volcano, but we're going to try some fizzy stuff, okay? Let me get this off here. I've got some of these. These are kind of fun. Bath drops. Whoops. Let's mess around with these for a bit, shall we? Okay. I've got to get a fresh flask here. Man, we've done all sorts of experiments today. Who knows? All right, let's get a little bit of a... Turn off that so we're not hearing the whiz. All right, I got some Evian water here. That's what we're going to pour in. Just so you know what kind of water we're using. In it goes. All right. And now, it looks like polychrome glass. All right, let's add one of these. There we go. I'm going to add a blue one. All right, in it goes. Let's just see how it looks. Fizzing away. So what's going on in this particular reaction? Let's see. I'm going to make sure I got this right. See if they got the ingredients. Yep, they got the ingredients right here. Sodium bicarbonate, so that's just baking soda. Sodium sulfate and citric acid. So what you're seeing there, the fizzing, is due to the reaction between the sodium bicarbonate and the citric acid. So the acid is providing protons to the bicarbonate. And when that happens, the bicarbonate gets converted into carbon dioxide and water. Thus the bubbles from the carbon dioxide. Where'd I get this liquid? This liquid is just water. This liquid that I'm looking at here is just good old water. That's all that is. I don't think this one's going to change color if I add acid, but I'm going to find out just for the heck of it. Here we go. You know what? I think I do see a bit of a color change. right where it lands. But not that much. Overall, I think that was kind of, oh, look at that. It's a little pretty. I can't get the focus right. There it is. I don't know, is the camera off, folks? Oh, where's my... There it is. Let's pop this back on here. Hello there, Kevin. Pop this back on. Get this rolling. Thanks, Air Friendly. I appreciate it. Thanks for letting me know. There's our static one. I can't make an egg parachute today. Yeah, Artur, I can make the other one spin, but there has been a request for me to leave that for a day and see what happens. Thank you there, Hiawatha. What I'm doing is I've added to this flask some universal indicator. That's correct, Yash. It's a neutralization reaction. Universal indicator displays these colors at different pH values. So we see this is kind of orange-red in color, and that tells us the pH in the flask is like 4 or 5. If I go ahead and add a little bit of acid to this flask, that should lower the pH. I'm adding acid right now, and we should see a shift to a red color. If I add base to the flask, the acid will be neutralized, and that will increase the pH, and that'll cause a shift to orange, yellow, green, blue, or violet, depending upon how much base I've added. Kevin, what other things do I do? Today we did some color separation stuff. So at the beginning of the live, we did some experiments where we looked at, how acetone and water, that's kind of a neat visual effect there, how acetone and water separate when you add salt. So I do salting out experiments. Here we go. Let's add a little bit of base to this flask. See if we can get the rainbow effect going on. Ooh, a little bit. There's your flash of the rainbow, folks. Can I make a coin spin just by using spoons and batteries? No, I can't. I'm not real sure anybody can. I can't, Hotel, and I think anyone who tells you they can is probably pulling your leg. Can I make the liquid a little bit different? What are you asking for there, Artur? Hotel, I can't. Please stop spamming the comments. I've answered the question 3 times now. I'm going to block you if it continues. I should have stayed in science class. Hey, thanks, Hiawatha. It was cool, wasn't it, Malkuth? Of Lux Flood. Yash, I apologize. I don't know what you mean by Lux Flood. So long, Kevin. Enjoy the other stream. Thanks for hanging out. How's it change color? Asked Pack Puncher. So Artur likes red and purple. So Artur, there you go. There's your red and purple, buddy. There's your red and purple. So how's it change color? It's complicated, but I'm going to give you a simple version of it, okay? So what you need to understand is that this indicator system has 4 different dyes in it, and it's the combination of those 4 different dyes that give you the color. I'm going to talk about one of the colors in there. One of the colors in there is called phenolphthalein. I'm going to go ahead and stop this and add some acid so we can see something that's going on while I'm yammering on about this, because this is a little bit complicated what I'm about to describe, okay? So phenolphthalein is one of the dyes that's contained in this particular system. And these are, I should say, I am 100% a nerd, Andrew. These are the different colors that phenolphthalein displays at different pH values. Absolutely, Hiawatha, please do. Thank you there, Asia. I do, Hotel. So this is how phenolphthalein behaves. It's usually colorless in neutral to slightly basic, and it turns pink at high pHs. So here's the way it works. When you're in an acid or even neutral, there's a lot of protons around. And we can imagine protons, we're going to imagine them by this cap, okay? And phenolphthalein is a molecule that's ring-shaped or open. And when it's ring-shaped, it is colorless, and when it's open, it's pink in color. The change in structure causes a change in color. Now, here's the way this works. If there's a lot of protons around, if there's a ton of protons around, what happens is the phenolphthalein molecule grabs onto those protons, and when it does so, it takes on the ring-shaped structure and therefore is colorless. This is in acidic solutions. If there's not many protons around, there's none of them for the phenolphthalein to bind to, and so the phenolphthalein does have nothing to grab onto, and so it pops open like that. And with that change in structure comes a change in color. And that's how we get these different colors at different pH values for phenolphthalein. Arturo wants rainbow. You got it. We're going to try it. Here we go. Turn this on. We're going to try the rainbow. The spinning in the liquid happens from, there's a little magnet down there, and it's on a magnetic stir bar, which is kind of like a magnetic stir plate, which is kind of like a magnetic fan. All right, we're going for the rainbow here. Here we go. I made it acidic. We're going to try adding some base here. Come on, baby. Come on, baby. Give me the rainbow. I think we got it. I think we got the rainbow, folks. The glorious rainbow. I do, Pack Puncher. I do. That's right, Pack Puncher. What makes it spin is the magnetic system. University. I teach university level. I've taught everything from like 6th grade up through some graduate courses at university. It is kind of neat there, Dane. I agree. All right, I'm going to tell you what I do near the end of the live is I flip the camera around and you get to see my old ugly mug. I'd love to have you be my new student there, Marlo. So if you don't want to see a 57-year-old man in his basement, then now's the time to get off the live stream. How are those rainbow transitions occurring spontaneously? I'm not 100% sure what you mean by spontaneously. Okay, quiz. What element in the periodic table is listed for iron? Fe, right? Thanks, Artur. All right, here we go. Time to flip the old camera around. Say hello. Let me turn this light on. See how folks are doing, and then we're gonna say goodbye for the rest of the evening. How do the colors and light get separated through a prism? So when light goes through a prism, light interacts with matter. And how the light interacts with matter depends on the wavelength of the light. And the different colors of light that we see have different wavelengths. And what happens when it goes through a prism, the long wavelengths get bent more than the shorter wavelengths. And the colors of the rainbow, this isn't the pH scale now. I just want you to look at these colors of the rainbow. This is the longest wavelength of the colors that we see. Next longest, and so forth, down to the shortest wavelength of the colors that we see. And because the different wavelengths get bent differently by the matter in the prism, the red gets separated from the violet and so forth along its straight line path. Thanks, there, Hiawatha. Dane, all I used in my color changing liquid was universal indicator, and then I added in water, and then I added either 20% by weight sodium hydroxide or 20% by weight sodium chloride. All right, folks. Well, we're going to call it a day. My wife is home. I haven't seen her all day. She just got home from work. I'd like to spend some time with her. So thanks for hanging out, and we're going to see you next time, okay? Artur, I usually do streams Friday, Saturday, or Sunday, and today I decided to do it on Sunday. Thanks there, Leon. You all have a great day, and we're going to see you next time.